Doing Every Challenge question, part 45. This is Core Pure 2, chapter 2. It's this series chapter, it looks like. So given this, find this. Well, okay, well, let's combine these two things together in the fraction here. This is r plus 2 over r plus 2. Combine them to make this. Then split the log into being log of this minus log of that, because of course that's how logs work. When you put in the numbers here, you'll notice something happens, which is when you use 1, you get log of 4 minus log of 3. Then you use r as 2, you get log of 5 minus log of 4, and so on. And everything is going to cancel except for the very smallest one, which is log 3, and the very largest one, which is log 33. So it's just log 33 minus log 3. It's called a telescope, I guess, and you divide them through based on the log law, this one backwards, and you get log of 11, which will be the answer. Next one, also kind of nice and straightforward. You just need to split this up. You can use partial fractions to do that. Very quickly, going to times this across there, times that across there, make 18. Of course, the only numbers over here are 3a, so a must be 6, and of course, AR and BR must cancel, so B is minus 6, so you can write this as this. And now if you put the numbers in, this is a bit more complicated, but what happens is the smallest 3 and the largest 3 don't cancel, or in terms of denominators. So 6 over 1, 6 over 2, and 6 over 3 has nothing to cancel with, but the 6 over 4 and the 6 over 5 and everything after that does. And then the other things that don't have anything to cancel with are the minus 6 over n plus 1, minus 6 over n plus 2, and minus 6 over n plus 3. And essentially, now we just need to get all this to look like this. There are probably much smarter ways to do this. I decided to combine these numbers. This is just 6 plus 3 plus 2. And then make the denominator the same for everything by timesing by the relevant denominators that I needed, and then taking away everything. There are probably much better ways of doing this. I expanded out some more. I compressed or collapsed everything together and got this, and this is nice. It factorizes out with an n, which is the form they wanted you to get it, so that was good. Anyway, the ratio test is something that you can learn lots about if you go to university and do maths. I'm sure some of the hardcore maths YouTubers will have made videos about this. I seem to remember Michael Penn making one at some point, but I might be misremembering that. Anyway, the ratio test says that the series converges if this happens, it diverges if that happens. It's sufficient. It's not necessary, but it is sufficient. Use the ratio test to show that the Maclaurin series. Now, I'm just going to say, because this video contains a lot of Maclaurin series, I'm just going to put these up on the board, and I'm just going to use the word Taylor series, because that's what we should be doing. So the Taylor series of the expansion of e to the x is this here. It's given to you in the book. I'm not going to derive that. If you want to derive Taylor series for e, sine, and cos, 3 Blue 1 Brown has a fantastic video doing all of that. Anyway, this is the Taylor series for e to the x, and I just want to show it converges. So let's take a term which is of the form x to the n over n factorial, and then the previous term is x to the n minus 1 over n minus 1 factorial. I'm just going to limit that as n goes to infinity. Technically, I guess actually I should have used n plus 1 and then n's here, but it doesn't make a difference. I'm sending n to infinity anyway. Anyway, this is a 4-tiered fraction. This one here goes here, and this one here goes up there, so we get this. This cancels to just leave an n on the bottom, and this cancels to leave an x on the top. But if n is going to infinity, this is always going to be less than 1, because you can't make x bigger than that. So this is less than 1, and therefore it's going to converge based on the ratio test. Use the Maclaurin series on this one instead. Now, we get given this, which is good. Sorry, I said Maclaurin, didn't I? I'm sorry, Taylor. I was just reading. Apologies, the Taylor series. Sorry. Anyway, this is the Taylor series for log of 1 plus x. Again, not going to drive it, it's in the book. So we're just going to take this term here. I think I actually did use plus. Yeah, on the second time I noticed I should have used plus 1s here. So this becomes an r plus 2. This becomes an r plus 1. That becomes an r plus 1 or an n plus 1, I guess, if you're sending n to infinity, which for some reason I am. I don't know why I didn't just use r. Who cares? It doesn't matter. And then the previous term on the bottom here. Now, these ones, because of this modulus sign, it doesn't matter that one of them is positive and one of them is negative. They're just ones, so I can just get rid of those. Again, 4-tiered fraction means this goes here and this goes here. The x's can cancel a little bit. You get this, and now again, it doesn't matter what the size you make x is. N over n plus 1 is just going to limit to 1. Actually, x doesn't depend on the limit, so you can actually bring it out to the front if you want to, like this, and then say, well, this just goes to 1. And so this sequence goes to whatever x is. So therefore, if x is between minus 1 and 1, it converges based on the ratio test. And if x is bigger than 1, it's going to diverge based on the ratio test. And that's all of that done. Really interesting question. Again, feel free to learn about the ratio test in your own time. the Lorentz factor, which I vaguely remember doing at university, but only very vaguely, I just remember the name, is given by this formula. Some stuff is here. Find the Taylor series expansion of this. Okay, well, that's I'm going to get rid of the question because obviously it's taking up a lot of the screen. So we're just going to call f of beta this maybe. And we're going to do a Maclaurin series of this, or a Taylor series. This is technically a Maclaurin series because it's evaluated at 0. So I guess that's actually what I'm doing here. It's a Taylor series evaluated at 0 is what it is. So we're going to do a Taylor series of this evaluated at 0. F of 0 is obviously just 1 over root 1, which is 1. Now, I'm going to need to find f dash, f double dash, and so on. I'm going to actually have to find f dash 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 because I think it asked me up to x to the power 4. Is that what it asked me to? Yeah, sorry, b to the power 4, I guess, whatever. Which is going to be a bit annoying. I just decided to do a load of product rule. There's probably much smarter ways of doing this that I didn't realize, but I thought I may as well practice some product rule. So this is actually just chain rule coming down here. So the minus half goes to the front. The derivative of that is minus 2 beta. And then you drop this down by 1. Then you start using product rule, right? So this all cancels to make a 1. Beta differentiates away and just left with this. And then you leave the beta alone and differentiate this to get a very similar thing you did the first time. Then you differentiate again. I mean, this is just chain rule to get down to here. And then differentiate away the beta, it just goes away. Sorry, actually, this is when you collapse all this together, it's a 3 beta squared, which differentiates to 6 beta, leave this alone, and then leave the 3 beta squared alone and differentiate this for that. And then I basically didn't want to differentiate that again. So what I did was I started substituting in f of 0, f of dashed of 0, and so on. F of 0 is clearly just 1 because it's 1 to the power of something. F of dashed of 0 is 0 because this beta forces it to go away. F dash dashed is 1 because this term goes away here, but this term still exists and it's just going to be a 1. And then f dash dash dashed is just going to be, well, this term goes away because of this beta, this term goes away because of this beta, this term goes away because of this beta, it goes to 0. And now I think in my head I can just say, okay, well, if I differentiate this, obviously these minus 2's cancel, so we just get 3 beta at the front. When you differentiate the beta, it just goes away, and you get 3 lots of this thing here. So I'm not going to write that down, but I'm just going to say, when I put in 0 to that, I'm just going to get 3 lots of 1. So this is just going to essentially differentiate and then turn into a 3 when I substitute in 1 because of this 3 here. Now this beta, when I do product rule here, by the way, when I do the second half of product rule here and differentiate this bit, substitute 0 would go away because of this beta. Now here, when I differentiate this beta, I'll get 6 lots of this, which is 6 when I put in 0. And then when I differentiate this guy, beta will stick around and make the whole thing 0. So I think I'm going to get 3 lots of 1 here and 6 lots of 1 here. And this is just always going to create 0 because you've got 3 beta squared at the front, along with some other numbers that I don't really care about. And whichever way I do product rule here, there's still going to be betas hanging around at the front, so that's all going to go to 0. So I think this is just going to be 9 when I evaluate it. Just the 3 from here, from the first half product rule there, and the 9 from there. That honestly would have been faster just to write out rather than explain what I was doing, but I just didn't want to type it up. So anyway, f dash 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 dash, I think I said too many dashes there, of 0 is 9. Cool. So now I think I'm ready to use the Taylor series evaluated at 0, and I can just say it's this. Which of course I can condense down. I don't need these 2 times, and that simplifies, and I get this here. So cool. That's the first part of the question, is that the theory of special relativity, which I do vaguely remember doing at second year, says something about time observed as t in the stationary frame will be observed as t over this Lorentz factor in a moving frame. I can't even remember what this letter is, so I'm just going to call it the Lorentz factor. I can't remember its name. Anyway, so okay, we have 4.2 light years away to the observer in the stationary frame, which is Earth. It took 20 years. So big T is 20. The Lorentz factor, now 4.2 light years away, that's a distance. Light years is a distance. It's the amount of distance light can travel in a year. So I think we can work out the speed of this by just doing speed equals distance over time. So the distance is 4.2 times 3 times 8, 10 to the 8, because that's how long it takes to do... okay, this is wrong. Okay, I'll explain this. 4.2 times the speed of light is the distance that this is. And 20, the distance, so that's speed equals distance over time. The time is 20 years. Oh, no, it's not wrong. It's fine. Is this. Sorry, this is fine. So V is 0.21 C. I've just written this as C. So that was what I was confused about for a second. Okay, cool. So if V is that, then when I divide that by C, I just get beta as 0.21. which is cool. So that means I can put that beta into my expression here that I've worked out and just throw it in there, and I'll get this number here. And then that's my gamma. That's whatever letter this is. I almost call it gamma, but I don't think it is. That's this number here, isn't it? Well, at least that's the estimation for this number. So now I can just do that original 20 over this number here, over this here, and I'll get my amount of time for the person on the spaceship. Calculate the percentage error. To do this, we're just going to find out the true value by using this here. So that's beta is still 0.21. So let's just put 0.21 into there, and we get this. And now I did 20 over this is this, and then I just compared these two things. So, okay, well, I just need to do the difference divided by the true value times 100. I just type that in. I put these numbers in the memory of the calculator, because otherwise, of course, they're just so close that the rounding will make a big difference. And you just eventually get this. That's kind of boring. Comment on your approximation would be more or less accurate if the spaceship was traveling faster. If the spaceship was going faster, then this would be bigger, which would make beta bigger, which means in this estimation here, beta to the 6 and beta to the 8 would matter more. So your estimation would be further away from the true value, I think is, yeah, cool. Last one. Given the Taylor series of e to the x is valid, here's the Taylor series for e to the x. Show using expansions, Euler's relation here. So, okay, well, e to the x is this. Let's just throw in an e to the ix. E to the ix is this. You just put i's everywhere. I squared is -1. I cubed is -I. I to the 4 is +1. So we end up with this funky thing that goes plus, plus, minus, minus, plus, plus, minus, minus, with i's every now and again. All we need to do here, that's the left-hand side. All we need to do here is say that I sine of x, if we look at this one and just times everything by I, is this. That's just literally timesing every time by I. And then you notice, well, okay, actually, this here, this term, this term, this term, this term, perfectly match up with cos. And this term, this term, this term, and this term perfectly match up with I sine. So therefore, this is equal to cos plus I sine, and that's literally all you have to say. Deriving, of course, these Taylor series is much more interesting. The much more interesting part of that. Again, 3 Blue 1 Brown has a great video doing that, which is great. So you should watch that.